All right. Thank you very much to the organizers for inviting me to this program and this meeting. It's been great. I want to try to describe some dynamics, simple dynamics, response functions, describe some of the experimental stuff that's been done in cold atoms and nuclear physics, and try to make some connections between the two. In this work, I've had many collaborators. I probably won't be able to credit them all, but for sure in the things I'm going to talk about today, it's this group of people who are really outstanding. So I'll start by giving a brief review of the static properties of the unitary Fermi gas, two components, infinity zero range. Say something about dynamics and response functions, then discuss some response functions at low momentum transfer in cold atoms. That's typically RF response. There's a variety of examples in nuclear physics of that kind of low momentum transfer reactions. The one that's probably most analogous is neutrino rates in dense neutron matter. And I'll briefly describe that and show some similarities and some contrasts between the two. And then I'll talk about high momentum transfer. In nuclear physics, that's often electron or neutrino scattering these days. You exchange a boson where you can measure the final state lepton, at least in some cases, and tell what the momentum transfer was. And it's somewhat analogous to Bragg scattering in cold atom physics. Doesn't seem to be working, so. As has been mentioned, Beera talked about, among many other things, unitary Fermi and Bose gases. We're going to take a Hamiltonian, which is just non-relativistic kinetic energy plus a contact interaction for the cold atoms. And we'll have finite range potentials for the nuclear physics stuff I'll talk about. And in nuclear physics, mostly we're interested in zero temperature or close to zero temperature and reactions on nuclei. Of course, there are exceptions to that. For the unitary Fermi gas, all quantities are constant times the free Fermi gas quantities, equation of state that Beera mentioned, the Birch parameter, the superfluid pairing gap at zero temperature, basically the energy to flip a spin. And what's got a lot of attention in both the cold atom and the nuclear physics community is the contact from Shinatan. It's basically the pair correlation function at zero separation. It also describes the momentum distribution at high momenta and things like the high energy tail of the RF response. There have been a lot of both experimental and theoretical works on that. So let me just mention a few things about the Birch parameter and the equation of state. This is, of course, a non-perturbative problem. We calculated in the continuum using diffusion Monte Carlo on the lattice using auxiliary field Monte Carlo, the Birch parameter and the equation of state on the left from 38 to 66 cold atoms on pretty large lattices up to 27 cube lattices. So we reached a pretty dilute limit. We have a branching random walk in imaginary time. And so we can go out to pretty large times and get to pretty cold temperatures. And we got this value of 0.372, which agrees with the experimental results. On the right, we also expanded the energy for finite effective range using different lattice parameterizations. We can implement different positive and negative effective ranges. And we plot those, the Birch parameter versus the effective range, KF times the effective range on the right. So the spin excitations, I'm going to talk about the RF response, so it's good to talk about the spin excitations. The pairing gap is quite high in this system. Everything has to be the Fermi, related to the Fermi energy. So in some sense, that makes the problem a bit easier. The gap that we calculated using diffusion Monte Carlo, we basically just have an extra odd particle, which is unpaired at different momenta. It shares in the simulation its momenta with the rest of the system. But we get a pairing gap as a function of this momenta, so essentially quasi-particle energies, which looks like that dispersion there at the minimum if it's slightly less than a half the Fermi energy. And the minimum you'll notice is below the Fermi momenta, a little bit below, around 0.7 or K min squared over Kf squared of 0.8. And then you can measure that in a variety of ways. One way that's been very sensitive is to look at just spin polarized systems in a trap. And what you'll see in a trap is in the central region where the density is very high and consequently the gap is very high. They'll have equal number of up and down spins. But in the exterior, you go to a polarized state where the single particle can go into this a little bit into the central region, and that tells you something about the energy of the quasi-particle. And those measurements agree with the calculations, or the calculations, I should say, agree with the measurements. We also did a bunch of work on the equation of state of neutron matter, so to try to compare neutron matter and cold atoms. This is work with Alex Gazerlis. And normal neutron matter, relevant to neutron stars, is fairly high density, so you can't ignore the effective range. But at very low densities, here up at the top is Kf. This is the equation of state for cold atoms, and this is what you get using some kind of traditional nuclear matter, neutron matter models, which have an effective range. And you say it starts to diverge a little bit. But still, the energy over the Fermi gas energy is very close to this value of a half. This is as a function of KFA, so you haven't reached unitarity yet. You've just gone to KFA equals 10. More recently, we calculated the density functional from many-body calculations of the static response. So we just put a periodic potential on the system and look how the matter changes. This is for cold atoms. And there's just a few parameters that describe this system. Stefano will talk about it. But you can calculate those parameters, and the parameters that go into the equation of state for finite momenta external potentials. And you can compare that here to the local density approximation. So you see you have a little bit of repulsion coming from the inhomogeneous beyond what's in the local density approximation. So Stefano will talk about that and also about comparing this to what results in few body systems, so going from few to many. Recently, we've calculated the pairing gap in neutron matter to compare to cold atoms. Here, it's quite a bit different. Delta over EF peaks very low in this KFA, or the density, because of the finite range of the interaction. And it gets to about 0.35, never totally up to 0.5. But nevertheless, there's a significant pairing gap in low density neutron matter. And we've calculated it at higher density using more realistic potentials, and calculated it using diffusion Monte Carlo, which we can do for some interactions, and auxiliary field Monte Carlo, diffusion Monte Carlo, which uses Monte Carlo to sample the spins. And that dashed line there is the BCS theory, and we get quite a suppression from that, which extends through the maximum and reach back to a minimum around Kf of 1.3 inverse Fermis. That's still not nuclear saturation density, which is a little bit higher than that. So the interesting thing that makes a lot of connections between statics and dynamic properties is Stan's contact. I'll just show some QMC results here. On the upper left, of course, the original thing was the energy as a function of KFA that has a slope, and that's given by the contact of probability of two particles being on top of each other. On the bottom left is a momentum distribution function. And beyond k, this is multiplied by k to the fourth. So beyond k over kf around 2, you get a flat constant as predicted by tan. And that momentum distribution function often comes in theories of response functions, particularly things like incoherent response from the Bragg scattering. And on the right-hand side is the pair distribution function. You can see it's very strongly peaked towards r equals 0. That vertical line there is the radius of our potential, and the expected behavior is just that 1 over r squared, and in the inside we multiply by kfr squared, so it should go to flat. And as a function of kfr, you can see the contact there. There's a very, now I'll move on and try to talk about some cold atom and nuclear physics response functions. There's a very nice review paper on some of the cold atom stuff. Spectroscopic probes of quantum gases appeared last year in Nature Physics. They talk about RF response and the Bragg spectroscopy. I'll connect those to neutrino emissivity of neutron matter. And for the zero momentum transfer, it's somewhat analogous to RF response, although it's different. And for Bragg spectroscopy, I'll talk about electron and neutrino scattering. Those two processes are often, in nuclear physics, it's of course controllable to quite a degree. There's also low energy response. But if you're looking in the quasi-elastic region where you think you're mostly scattering off of one nucleon, it's very similar to that Bragg spectroscopy, which is typically done often done at 4 or 5 times the Fermi momentum. So it's a very simple expression. It's very difficult to do any kind of quantum dynamics, as many people know. There's been some nice talks here about particular applications. But one of the, in principle, should be easiest things to do is to look at dynamic response functions, and I'll talk about cold atoms and nuclear physics. So in general, you can write it as just a 2-point correlation function with a real-time evolution. That's hard for us to simulate because it's real-time and has a lot of phases in it. You can also write it as a sum over final states with particular energies and a delta function in energy conservation between the difference between the final state and the ground state energy and the delta of omega. I'll talk basically about zero temperature here. It'll be simpler because the nuclear physics experiments are done at zero temperature. There's a static structure function, which is just indicating the response over omega. That you can't really do in nuclear physics because you pretty soon start exciting deltas and making pions and things. But it's a useful concept, and it's very useful, particularly in cold atom and other physics. So there's two kind of excitations I want to talk about. One is low momenta, where you have, in principle, collective oscillations. There's a lot of literature on this. One thing you can calculate kind of exactly is the sum rules, energy weighted sum rule, and if they exist, higher energy weighted sum rules, assuming you can calculate the ground state exactly. You can also use a susceptibility if you don't have a superfluid to give you the 1 over h sum rule. Often you know also the threshold for a finite response, and the h0 sum rule is, of course, just the static structure factor. In nuclear physics, the energy weighted sum rule provides a lot of information about the interaction in the dynamics, which is beyond what typically happens in simple cold atom physics models, because the charge and the currents move with the interaction, and you're don't have just single free particle interactions and contact interactions. In nuclear physics, the long wavelength interactions are often done in RPA. there's a lot of work that in chemistry also. An old paper by George Birch summarizes this, which is shown here, some of the RPA work. A lot of low energy electron and neutrino scattering where you look at collective excitations or low-lying excitations in the nucleus is described here. Here's a very recent work on RPAs and quantum chemistry, and which was illustrating things. This can couple to things like density functional theory, so it's very valuable in quantum chemistry. I won't talk about that really. For higher momentum transfer, it's pretty much a local operator. For higher energies, you can't go too far in time. The time has to be short. And so it's basically this 2-point response correlation function is J dagger with a real-time evolution in between with some kind of current operator, which depends on the type of response you're looking at. So there's a long history of this kind of work for different operators, different applications, neutron scattering and condensed matter, electron scattering in nuclear physics, and more recently neutrino physics. They exploit this locality and a factorization of the physics right around the vertex, right around where the electron exchanges a boson with the nucleus. There's historically a lot of work on Y scaling, which is just the longitudinal momentum distribution of the nucleon, and spectral functions and contact. I think Nir will talk about the contact and how you can use that for electron scattering and neutrino scattering. We've also done work on imaginary time response. This is easier to calculate. Real-time response is very difficult. This gets rid of some of the interference, and we can do this for a certain imaginary time with full final state interactions and full currents. The longer imaginary time gives you more information on the low energy part of the response. And if you have a very smooth shape of the response, you can do some kind of inversion, which in these kind of problems you often do, but in many cases you don't. There are other approaches. Sonia Baca has worked on Lorentz transforms and coupled cluster doing longitudinal response in calcium-40 recently. I won't talk about that, but it's the similar ideas. But I will say again, nuclear physics, the interaction can be important in moving the charges and currents. You can see if you have up here J dagger J, if this Hamiltonian moves the current, exchanges the charge between two nucleons, that could have a dramatic effect on the response. Okay, here's some plot of the RF spectra, low, near zero momentum transfer. This is Weierlein from MIT's work. This is as a function of temperature. At high temperature, it's peaked around zero. You have a lot of thermal broadening of the system. At low temperature, you have a peak here, and it's comparable to the Fermi energy of the system. And this is that line shape for the low temperature. And this omega to the 3 behavior at high energy is telling you about the contact. This is the spectra at low temperature. This is at extrapolation. This particular figure is polarized system versus unpolarized. So all paired versus not all paired. But by extracting this slope, they can tell the contact and the condensate fraction versus temperature. And they can get down to about 0.1, the Fermi temperature. And you can see they get a contact around 3 or a little higher, and a condensate fraction of around 0.7. So it's a huge condensate fraction compared to helium or anything like that. Liquid helium I'm talking about. So the analogy to this in nuclear physics is neutrino emissivity in neutron matter, which is relevant to the cooling of neutron stars. So it's most relevant because you, of course, have two species here in nuclear physics. They have close to infinite scattering length. However, they do have an effective range, which is important. So what we did some time ago was calculate just 3 sum rules. We calculated the static structure factor, which is here. This is the spin-spin correlation function at about a Fermi. The two neutrons like to have opposite spins. And this is the static structure factor you get out. The energy loss rate here is proportional to this response with this omega to the 6 e to the minus omega over t s of omega. We're assuming here that we're above the transition temperature. The superfluid transition temperature in neutron matter is of order in MeV. So before you cool down in your neutron star to that less than an MeV. And we are really sensitive in this to the strength below about 50 MeV. That scale is set by the cooling of the neutrino, the energy of the neutrinos in the dense matter. And they can propagate or not, depending on the strength of this curve under about 50 MeV. There's no process by this time that's making neutrinos of order 100 or 200 MeV. And this is the shapes that we get out. This is for different densities. The middle one here is approximately nuclear matter density, so rho of 0.16. And this is a function of frequency in MeV. So you can see it's about peaks at around 40 or 50 MeV, and it's very wide. This is basically a result of having an interaction. If you put an interaction that didn't have any spin dependence in it, was just a radial dependence, the energy weighted sum rule will be just k squared over 2m, and k is close to 0. So this width wouldn't be there. This is width has really been given by the final state interaction more than the gap. The gap is much smaller here than it is in cold atoms. So you're sensitive to that, but not as much. And this is a calculation relevant to the normal region above the superfluid gap. But you can see that nevertheless, the response has a width of order the Fermi energy. At saturation density, Kf is about 1.7 inverse Fermi, so the Fermi energy is about 60 MeV. So you're right there on the curve. And you have a response over a wide range of energies in the system. If you did the density response, just coupled to all nucleons equally, it would be much lower peaked. The other kind of thing that we've had a lot of interest in is the Bragg spectroscopy experiments. These particular ones that were done at Q of order 5 KF. There you can see, depending on where you are in the BEC-BCS transition, you can see 1 peak or 2 peak. If you're deep in the BEC, you just see 1 peak for you propagate bound pairs. But if you're at unitarity, you see the 2 peaks. And you can measure the contact, and you can measure the full static structure factor there. And this is just a quick plot of versus magnetic field. So you're going from the BECS to the BEC, and you can see you shift from one peak to the other. And basically you're propagating these pairs as you go more into the BEC, but in general you can have both. And this is from the review article where they show it at the top exactly at unitarity, and the bottom curve is at KFA equals 1, so in the BEC regime. And this 0.5 is units of Q squared over 2m. So your peak is right where you expect it to. So this had been predicted by Sheena Tan in some operator product expansion. I won't go through all of this, but if you do electron scattering, you can couple to nucleons also with a high momentum. And 2 things have been noted about this. One is scaling. You're very sensitive to the momentum distribution or the spectral function of single nucleon scaling. This is for a whole host of different nuclei. And on the left, you're basically not doing inelastic scattering to pions or deltas. So all nuclei look more or less the same. And on the right, of course, it's different. The thing that is distinct, though, in electron scattering is you can't just totally treat it as incoherent scattering from single nucleons. Because if you divide by the single nucleon form factors and you compare the longitudinal, which is the charge scattering, to the transverse, which is the scattering from the currents, you can separate that experimentally by doing different kinematics. And you can see one peaks here and the other one peaks about 40% higher. So it's more than just scattering off of single nucleons. Even if you looked at the response, it would just look like a simple broad peak like you would expect. And this has been done in imaginary time formalisms. This is longitudinal on helium-4 quite a long time ago. If you just did the momentum distribution, you get this solid curve. And this is transverse scattering on carbon-12, which was done more recently, which is a lot more difficult. We're not exploiting any factorization here. We're just doing the full imaginary time evolution. And the blue curve here is the full calculation with 1 and 2 body currents. They interfere, which is the dominant correction here, and gives you a much better description of the experimental data. So neutrino scattering, people want to do this for oscillation analysis and neutrino scattering, and the dominant thing they want to look at now is parity violation, not parity violation, CP violation in neutrino scattering. And this is our expected signals versus neutrino energy. These dashed areas are the fluxes for 2 different kinds of experiments versus energy. You can't really separate these. You'll get all these neutrinos at once, unlike electron scattering. But the signal of the CP violation will be peaked from neutrinos here at around 0.8 GeV in this experiment and a few hundred MeV, and similarly here. So you'd like to get that response as accurately as possible. And we've done that recently with calculations on carbon-12, where we've looked at T2K and mini-boon. And this is some neutral current scattering. Again, the 2-body interfere with the 1-body, and they give quite an enhancement in some cases. And let me just conclude by flashing up. Recently, we've been doing this in the short time of what we call short time approximation, which we just propagate 1 and 2-body parts of the full system, exploiting this factorization. And we can calculate these 2-body interacting propagators exactly by summing and sum over all these final response. What we get in the full cross section, you have the square of the matrix element. So you can either have this 1-body current, which dominates, but these 30% corrections can come from either momentum high energy pieces of momentum distribution from a strong interaction, or from 2-body pieces of the nuclear current, which come from exchanging pions, for example. And that seems to be working well. And this is a comparison with the full imaginary time calculation. So here's the conclusions. I think there's a lot of dynamics, which is generally a difficult problem that we can address in linear response. There are analogs between nuclear physics and cold atom applications. We can see few body properties. These pairs propagate in the cold atoms, and we can see 2 particles propagating in nuclear physics as well. The exact dynamics is a bit different, because in one case, they're very strongly paired, in the other case, not so strongly. It's very important to improve our abilities to do these applications for things like astrophysics and neutrino physics. Monte Carlo methods have some unique strengths and challenges, and the improved theory of the response has many important applications. And it's one thing we're also trying to do with quantum computing, because at least at high energy, you don't need to propagate too far in time. Okay, with that, I'll finish. Thank you.
Questions?
Very nice talk. I guess I missed when you talked about this Bragg spectroscopy of the Chris Vail group with the two peaks. You mean the Bugluer mode on the BEC side and then this pair breaking continuum on the BCS side, or what do you mean with the two peaks? And did you model that with your calculations or not? I missed that.
Okay, we have not yet modeled that with those calculations. We couldn't figure out how to do it with the full imaginary time, but we can do it with this short time approximation. So the two peaks can appear if you shoot in a momentum transfer of about 4 or 5 times the Fermi momentum, you get both peaks at the same time. One is coming from, in this short time approximation, for example, the two particles that are paired propagating through the medium, and they of course have a higher, because you're injecting a big momentum, they have twice the mass, so they'll have a lower energy than if you strike one atom at a time.
But okay, I guess I mean, normally you would say that you have like a collective mode peak, which is the Bugluer mode or Bugluer-Anderson mode in the.
But these are at 5 times the Fermi momentum, so nothing's very collective here.
Okay. So then, okay, then I'm not sure I understand.
Okay, very nice overview. You have studied the low momentum transfer and the high momentum regions. And a low momentum, you say, okay, RPA, something like that, density, time-dependent density function. At high momentum, you use your approach, imaginary time. Could you comment in the region in between? So I guess that you can see how when departing from RPA is happening.
Yeah, I think you can work on improving RPA, and you can also work on extending these other methods to lower energy. And it's obvious as you get to lower momentum and lower energy, you're going to excite over a wider range of space. And you can go in nuclear physics from state to isolated transitions from one state to another. You can always calculate that matrix element if you can calculate the two states. But to get a continuum like this is more challenging. And to get to the low energy part of the response, where it's collective but not, more than just two nucleons, is not a trivial thing. I mean, maybe the couple cluster people can do that, but it depends on the momenta of the probe also, of course.
Can I ask further? Since you mentioned high order samples, you just mentioned, for example, H2 in your language. One of the problems is the high energy behavior of the response function, to know what the dependence of that. I think when you invert your imaginary time, you keep the existence of the second momentum fixed or not?
In the imaginary time calculations, we're doing it typically for a fixed momentum transfer.
Yeah, no. I mean, when you invert the imaginary time to get the response, you have to fix some rules with that you get that.
No, but we have finite. We always have a sum rule with e to the minus h tau, and as long as tau is bigger than 0, they're all converged.
Yes, so you keep that fixed.
Yeah.
Dependence on the existence of the sample. This I mean.
No, because we have finite time propagation. All the sum rules for our calculations exist.
Yeah, of course. Of course, they exist in that sense.
There are, of course, problems at high energy. In addition to the pion production, etc., there's relativistic impacts which should be included, which we have not yet included. But That's difficult to do in the many body simulation, but we're trying to do that in the short time approximation, which is basically a few body thing.
Thank you. So you mentioned this neutron emissivity in the neutron matter that also
Neutrino
leads,
emissivity, sorry, neutrino emissivity.
neutrino emissivity, yeah. So and that this leads to cooling of neutron stars. So I would like to just learn a little bit more about this. Has this been observed? And so it has to do with the beta decay, I guess. And so what's the rate and what happens to the star and how does it actually work, the cooling?
It's been observed, crudely in supernova. You see from one supernova, you saw some neutrinos, but only about 20. But that's when it's hot. You have a proto-neutron star, you have a core collapse supernova, you make a proto-neutron star, turns into neutron matter. The temperature of that can be tens of MeVs. And then you can, by various means, look at, once the neutron star is cooled down, what the cooling is too. Not if it's too old, then it gets below detection. But that's probably in the regime where it is superfluid, and you'd have to look at those more carefully.
I was wondering, some years ago, had some work with Dorta and Seth Rittenhouse. We looked at 3 and 4 component Fermi gases at negative scattering lengths, and it looked like there could be a many body collapse. Have you ever explored these regimes?
I have not. It's an interesting idea. I think to make it more likely to see that, you'd want some system where the 3 and 4 body correlations are strong, but presumably that could be arranged, at least theoretically, with the right choice of parameters. Experimentally, it's of course difficult to get too many attractors.
So, doing the calculation, you observe some dependence on the interaction you're using?
We've only used a few interactions. Mostly this is sensitive to pion stuff. So we're not at high enough momenta where we're terribly sensitive to either currents or correlations at some even higher momenta than that. We've turned off various pieces of the interaction and currents. And the biggest thing beyond the initial momentum distribution is coming from the pion correlations and the currents. That's why they can interfere and lead to the same final state, because the momentum transfer is kind of similar in the two processes. It's basically the same physics.
Any other questions? I don't see any. Let's thank Joe again.